So what we're going to examine today is something called special right triangles. Okay, these will grow to have more and more meaning for you as you progress in your math careers. All right, so I'm going to introduce this topic. You're going to talk about these special right triangles probably again in Algebra 2, and then definitely in pre-calculus you'll talk about these special right triangles, and then definitely in calculus you're going to talk about these special right triangles. Okay, in fact, you're going to know them so well, you're going to have them memorized because they kind of lead into a lot of stuff with trigonometry, and you'll be able to do mental math and stuff. So, but right now we're just going to introduce the topic, build up a good foundation. But you will see these for the rest of your math careers, except for statistics, I guess I'll say, in high school. I'm assuming a lot of you guys are going to at least progress on to pre-calculus and hopefully calculus as well. So yeah, you'll be seeing these quite a bit. So we're going to kind of introduce the idea here, all right? Because I don't think you've talked about these in the past. Maybe you have, but we'll see. So special right triangles. So the essential question we want to be able to answer is, what do you know about the side lengths and well, we're going to worry about trigonometric ratios later. We haven't talked about those yet. But right now we'll just worry about what do you know about the side lengths in special right triangles. Okay? So the first kind of special right triangle we're going to look at is an isosceles right triangle. Okay? And so we're going to look at some relationships that will always apply in isosceles right triangles. Okay, so this figure right here, okay, shows, the directions here say that it shows an isosceles right triangle. Okay, so we want to identify the base angles and use the fact that they are complementary to write an equation relating their measures. So let's see here. If you can remember base angles in an isosceles triangle, what that means. Okay, remember base doesn't necessarily mean bottom angles here. So I'm going to pick somebody, let's see. So Hunter, can you identify what angles in this triangle are the base angles? Okay, so angle A is a base angle. Oops. Base angles. Okay, so base angle, angle A is a base angle. Angle C, however, is not a base angle. It is on the bottom, but remember we have to be careful about the word base and bottom. Base does not always mean the bottom side, okay? In this case, it definitely does not mean that. So so then what's the only other option, I guess, then? That's right, by process elimination, you got it. Angle A and angle B. Now, why is it those two angles that are the base angles? Yes, Stephanie? Right, so these two sides, they're opposite the two legs. All right, so this side and this side are the legs. And what makes these the legs? What's that? Okay, so the right angle, that's part of it. If this were not, but here's the thing though, if this were not a right triangle and we still had this and this side congruent, if it was still isosceles but not right, these things would still be called legs. And so in an isosceles triangle, the congruent sides, or there's at least two congruent sides, these two sides are the legs because they're congruent. Okay, this third side in an isosceles triangle is called the base. So obviously, because it's also a right triangle, it's the base, or it's also called the hypotenuse here, right? But this is the base, these are the legs, and these make these the base angles. Okay, so Hunter, so now use the fact that they are complementary. What does it mean to be complementary? So what would be the equation I could write here?
Angle A plus angle B is equal to 90.
Yep, I'm going to use the measure of angle A plus the measure of angle B, since we're talking about their measures. That's going to equal 90 degrees. Yep, that's the equation we want to be able to write there. Good. Thank you, sir. All right, so then what else do we know about the base angles in an isosceles triangle here, Evan? What else will be true about angle A and angle B? Besides the fact that they're going to add up to 90 degrees, what's going to be true about their measures as well? They're equal. They're congruent. Exactly right. So we can also write that the measure of angle A is equal to the measure of angle B. Okay, base angles are congruent. So since we have these two equations here, the measure of angle A plus the measure of angle B is 90 degrees, and the measure of angle A is equal to the measure of angle B, how can I rewrite this equation? Let's go to, Zishan. For example, instead of writing the measure of angle B here in this equation, what can I write in its place?
45.
Okay, 45, that's right. Yeah, I was going to say, so you got one step ahead of me basically, but I was going to put measure of angle A in there for the measure of angle B, which would be then, if we add, so if I have measure of angle A plus the measure of angle A, how many measures of angle A is that? 2. So it's 2 measure of angle A equals 90 degrees. And then, yeah, we divide both sides by 2. We get the measure of angle A equals 45 degrees. And therefore, also, the measure of angle B is 45 degrees. You got it. Okay? All very formally, but most of you guys probably could have just seen that without having to write all this formal definition out. This is more proof-like, what we just did right there. And I know you guys don't like the P word, but, well, there it is. I just said it. Okay? So now letter D says, all right, so we got that. This is a 45-degree angle and a isosceles right triangle. That's a 45-degree triangle. Sometimes this triangle is called a 45, 45, 90 triangle because it's referring to its angles there, 45, 45, 90. Now it says, use the Pythagorean theorem to find the length of the hypotenuse in terms of the length of each leg, x. So that means we're not going to actually find actual measures, like, you know, the actual side length. We're going to find the length in terms of x. So our answer is going to have x in it. So, Mary, how could I set up the Pythagorean theorem here with what we've got? What would I write?
Okay, so put x squared plus x squared equals,
We'll call this maybe like c.
yeah.
So equals c squared.
Yep.
Okay. So we can simplify this a little bit, right? So for example here, what is x squared plus x squared?
X squared.
2x squared equals c squared. And again, I'm not interested in c squared. I want to know the length c. So what should I do both sides to get kind of c by itself here?
You take the square root.
Yep.
No, you find both sides by 2 and then you take the square root.
Well, we want to solve for c. So c is just being squared. So yeah, and I know it's kind of weird. We're not solving for x here. We actually want to solve for c. So we want to just get the c by itself. All the c has is c squared, so we square root both sides. And that leaves us with c is equal to the square root of 2x squared. Now, can we simplify this at all, Mary? Are there any perfect squares in here that we can kind of pull out? I see a perfect square. Yeah, x squared is a perfect square, isn't it? Right? It's x squared. So this is the same thing as saying the square root of 2 times, I know it's a little bit weird because we're dealing with variables being squared, but isn't that equal to the square root of 2x squared? Isn't that equal to the square root of 2 times the square root of x squared? Okay, and so Mary, what is the square root of x squared?
X.
Yeah, it's just plain old x. Okay. And so then c is equal to x times the square root of 2. Yes, question, Elizabeth.
How come when it says 2x squared equals c squared with the here, how come you didn't simplify the c like squared?
So like why didn't I divide both sides by 2?
No, why didn't you, like you, what's it called?
What do you want me to do to simplify this, I guess is my question. The square root?
Yeah.
Okay, right. So that's so I did simplify. The square root of c squared gave me c, and then I brought this over. So c is equal to that. So and then I simplified it. Okay. So there's the length of the hypotenuse in terms of x. So now anytime we run across an isosceles right triangle, if I'm given one side length, I know every other side length. Oh, and I just said that, and that was in the reflection question there. So the answer, yes. Okay. So is it true that if you know one side length of an isosceles right triangle, then you know all the side lengths? The answer is yes. If BC, for example, is 3, what does that mean AC's length has to be? 3. And what does that mean AB's length is going to be? Well, so if x is 3, right? And this x would also be 3, and so this x, it's 3 square root of 2. 3 times the square root of 2. That's all it is. 3 times the square root of 2. If BC is 4, what's AC going to be? 4, and C will be 4 times the square root of 2. That's it. Yeah. Okay, that's all there is to it. So we can, like, anytime we have one side of an isosceles right triangle, we can then find the other sides. Okay. All right, so let's continue on here. We'll skip that to what if. We'll go to the other ones. There's one other special right triangle. All right, and this other special right triangle is derived from starting with an equilateral triangle So triangle ABD is equilateral. And then drawing in a perpendicular from B to C. And then it's asked us to determine all three angle measures in triangle ABC here. All right, so let's do that. So I'm going to go to Michael here. So can you identify any angle measures here in angle ABC?
Angle C, which is 90 degrees.
All right, so angle C is 90 degrees. That's right. Okay, so angle C is 90 degrees. The measure of angle C is 90 degrees. How about anything else here, Michael?
No.
Well, so let's think about this. So yeah, maybe, because right now we're missing two angles here, but let's think about this. ABD is what kind of triangle?
An equilateral, so they both be 45 degrees.
Okay, careful. What are the angles in an equilateral triangle? What do they have to be?
They all equal the same measurement.
Right, which is? 60 degrees. So in triangle ABD, all the angles have to be 60 degrees, which means angle A is going to be what?
A is 60 and angle ABC would all be 30.
Yeah, how'd you get ABC?
Because it's a bisector, so split in half.
Okay, so we're not told it's a bisector, and we actually don't need to use the fact that it's a bisector. If I know that I have a triangle right here, and if this angle is 60 and this angle is 90, how can I find that third angle? Instead of using the bisector.
Just calculate.
Yeah, so try from 180, right? So yeah, you're right. But angle ABC is 30 degrees. Okay, and so this triangle right here is where we're going to be kind of, well, actually, I'll hold off here, and then we'll talk about that in a second. So, all right, letter B, explain why triangle ABC is congruent to triangle DBC. Ooh. All right, so let's see, I'll call on someone here. Let's go to Tanner. What do you say here? Why is triangle ABC congruent to triangle DBC?
Because angle, angle.
Okay, is angle, angle, angle a congruent statement?
No,
Yeah.
angle side angle.
Ah, angle, side angle. Where do you see angle, side angle here?
They both share BC.
Okay, they both share BC. That's a 30-degree angle. That's a 30-degree angle, so they're going to be congruent. And they both have a right angle there too, right? Yep, so let's see here. Angle, and I'm going to do like basically like a miniature proof here. Oh my gosh, I used the P word again. You guys thought we were through those proofs. You were wrong. Okay, so angle ABC is congruent to angle DBC. You know, I don't know, we can say both are 30 degrees. Sometimes I'm hurting a little bit for like fancy sounding explanations. Okay, and then angle, what, ACB is congruent to angle BCD. BCD, because, let's see, BC is perpendicular to AD. Right, and then BC is congruent to BC. And what's the reasoning, Tanner, for something being congruent to itself?
Because reflexive.
Reflexive property, you got it. And so therefore, triangle ABC is congruent to triangle DBC by, whoops, angle side angle. Okay. Good. Yes, proofs. Ugh. Terrible. We made it. All right. So we know those two triangles are congruent. So really, if I'm talking about this 30, 60, 90 triangle, I'm also talking about this one. They're the same thing, basically. All right. So Evan, you can see here we took ABC. So we started with this equilateral triangle here, ABD. We took this piece away, which is a 30, 60, 90 triangle. So that's what we'll refer to this one as, a 30, 60, 90. Just like the other one, the other special right triangle is 45, 45, 90. This is 30, 60, 90. Okay. So this length is going to be called X here. All right. So if AC is a length of X, remember again, we pulled that from here, so you could also call that X as well. Okay. What will the length of AB be here? Any ideas? No. Okay, that's fine. So let's go this way. We just said that this triangle right here is congruent to this triangle right here, right? So if AC is X, what does CD have to be? Sorry? x as well, right? Because corresponding parts of congruent triangles are congruent. So AC corresponds to CD. Okay, great. So what does that mean the length of AD is? 2x. So what does that mean the length of AB is? What kind of triangle is triangle ABD? Nope. It's equilateral. So if AD is 2x, what does AB have to be? 2x. That's right. 2x. So that means AB here, the same piece, is 2x. Okay. So again, let the length of AC be x. What is the length of AB and y? Well, let's see here. Let's see here. AD equals x. And, sorry, not AD equals x. CD equals x. And therefore, AD equals 2x. And so, AD is equal to AB. So, AB also equals 2x. Something like that. Okay. All right, so now using Pythagorean Theorem, we're going to find the length of BC. Actually, any questions so far up to this point? I don't want to leave anyone in the depths. Tangent slower, yep. Okay, so Julia, using the Pythagorean Theorem, here in part D, okay, asks us to find the length of this segment BC right here. All right, so again, Pythagorean Theorem, it's a squared plus b squared equals c squared. So what do I put where? Like, what's the hypotenuse here, for example? 2x. So that means I got to square 2x, right? It's going to be the quantity 2x squared. And then what's one of my legs here that I know? Yeah, so we'll just have x squared. And the other one we don't know, so I'll just call that like b, I guess, for right now. So plus b squared. And we want to solve for that length b here. So let's see, how can I simplify 2x squared, Julia? What is that going to become? 4x. Yeah, squared. The 2 and the x get squared there, right? They're both in the parentheses, so that was right, 4x squared. And I have x squared here plus b squared equals that. So again, I want to solve for the b here, Julia. So what should I do next to get this, to help start getting this b squared by itself?
X squared.
You got it. Okay, so if I have 4x squared and I take away an x squared, how many do I have now? 3x squared, that's right. So I get b, I'm going to put this up here. So I get b squared equals 3x squared, and then to finish solving for b here,
Find the
square root of both sides, you got it. Okay, so square root of b squared is b. Square root of 3x squared, can we simplify that at all? Are there any perfect squares in here? What do you say, Julia? Yeah, that's right. Yep, same thing as before. So it becomes the square root of 3 times the square root of x squared. And what is the square root of x squared, Julia? X is right. So it's x times the square root of 3. Okay. So this is x times the square root of 3. All right, so that means that if I have any side of a 30, 60, 90 triangle, I can find the other parts, the other sides, the other pieces. Okay? So for example, if I have this short side here, and I say it's a length of 2. So let's say AC is a length of 2. Okay, so just hypothetically here, if AC is a length of 2, then Elizabeth, what does AB have to be in length? 4, yeah, you just twice that x value. So if this is 2, that's going to be 4. And then what is BC's length going to be? Times. That's it, yeah, that's right. Yep, that's it. All right, so now if we go down here, we're going to skip this, reflect. We're looking at number 4. Explain the error. A student has drawn a right triangle with a 60-degree angle and a hypotenuse of 6. He has labeled the other sides as shown Explain how you can tell at a glance that he has made an error and how to correct it. So, do we have an error here? It looks like our x value here is supposed to be 3. The hypotenuse is twice that, 6. What should this side be? 10? 3.
Yeah.
3 times the square root of 3. Okay, so that's the error. It should be 3 times the square root of 3. If the short side is 3, that's the x, right? It's because it's opposite that 30-degree angle there. That's the short side, so that's the x side. The hypotenuse is going to be twice that, and then the side opposite the 60 degrees is going to be x times the square root of 3, the short side times the square root of 3. Okay? You will need to have these two triangles' relationships memorized. So the idea is that, like, the isosceles, I won't be able to give this to you, right? You will need to have this down. The 45, 45, 90 triangle has this relationship, x, x, and then x times the square root of 2 for the hypotenuse. And then similarly for the 30, 60, 90 triangle, it's going to be x for the short side, the one that's opposite the 30-degree angle, and then 2x for the hypotenuse, and then x times the square root of 3 for the other leg there, opposite the 60-degree angle. Okay, you will need to have these down. I can't give these to you, so you'll need to know them. Okay, on a future test or a quiz, you'll need to have those relationships memorized. Okay, you can derive them. Okay, you can derive them, but by using Pythagorean Theorem and stuff like that. But you need to have those down. Alright? So, let's actually see this put into practice. Alright, so turn the page here to 711. Okay, and we're going to look at example. So, and there they are again in all their glory. Okay, so again, you need to have these memorized. Okay, you need to know those. I am not going to be able to give those to you on a test or a quiz. And the reason why I can't give them to you on the test or quiz is because we can't give them to you on the benchmark. And I want to practice like we're going to play. Okay? Practice like you play. So we need to know these. All right. So we'll scoot down here to actually see this in action. So here we've got an isosceles right triangle, right? It's the 45, 45, 90. And so we want to take a look here. This 10, okay, this 10 corresponds to what part in my formula kind of triangle here? What does that match up to? Well, it's the hypotenuse, right? It's opposite the right angle, and so I'm going to go up here to my 45, 45, 90, and I see that opposite the right angle is x times the square root of 2. So that means this 10 is equal to the x times the square root of 2 part. All right, so it matches up with 10 is in the position of that x times the square root of 2, so that means this 10 is equal to x times the square root of 2. And I want to use this then to find these two missing parts, which are both corresponding to the x. They're equal to the x measure. Okay, so we already have the hypotenuse. I just have to figure out what the x is in order to know what these side lengths are. Well, according to this little equation, what do I need to do here to get what x is? What must I do to both sides to get x by itself here? Drew, what do you say? If I just want to get x, what should I do?
Move the square root of 2 onto the side, so subtract the square root of 2.
So is this x plus the square root of 2 equals 10?
No, so divide.
There you go, right. It's x times, so we're going to divide both sides. So I'm going to write that little work over here. So we have x square root of 2 equals 10. I'm going to divide both sides by the square root of 2. Okay, so x is equal to 10 divided by the square root of 2, which, that's kind of funky looking, but we'll try putting it into our calculators and see what we get here, see if we get something nice. We get a decimal. So we can say it's about 7.1. Okay, it's about 7.1, but we actually have to do a little bit more work here. Okay, we have to do something called rationalizing the denominator. Did you guys do that at all in Algebra 1? Okay, so, and I'm not really sure why. I should look this up. But for some reason, it's bad to have square roots in the denominator. Okay, so we have to get rid of that. And the way we do that is we take 10 over the square root of 2 and we multiply. We want to multiply square root of 2 by something to kind of get rid of the square root. Well, if I multiply square root of 2 by another square root of 2, and square root of 2 on top. Okay, you remember doing it then? Okay, well, maybe, so some of you guys maybe remember, okay? That's cool. How about my 9th graders? You guys remember this at all? You guys get to see this? No? Okay, no? Okay, so this is, and again, I'll tell you this, when you get to calculus, you won't have to do this again. You won't have to do it. You can leave it as 10 over the square root of 2, but for whatever reason, we have to rationalize the denominators, okay? And so that's what we got to get rid of the square root. And we do that by multiplying both sides by root 2 over root 2. Now, why is it okay for me to multiply by root 2 over root 2? What is this really equal to? What is square root of 2 divided by square root of 2? It's 1. And I can multiply anything by 1, and it does not change the value here. And so 10 times the square root of 2 is just 10 square roots of 2. But what's the square root of 2 times the square root of 2? Well, let's check my calculator. It's 2. So it gets rid of that square root in the denominator. And then we can divide the 10 and the 2. That's right. So 5 times the square root of 2. And wow, that's our final answer. You need show all this, you mean? So if you feel comfortable doing that and you can do it consistently, then I don't care. But if you're going to have trouble with it, then I want you to show that. If you start making mistakes, then yes, I want you to start showing it, because otherwise, I don't know how you're going to correct yourself. Okay? All right. Questions on any of that? That was a bit much, I know. I just threw a bunch of new stuff at you there, but I think we can handle it. So let's try another one here. Let's look at letter B. Okay, now, letter B. All right, we're now dealing with a 30, 60, 90 triangle. All right, so we have to kind of orient ourselves here. I don't know if I can fit both things on there. I can't really, so I'll just draw it. Okay, so from the top, we have that the 30, 60, 90 triangle, the hypotenuse is twice x, the shortest side is x, and then the middle side, the other leg, is x times the square root of 3. Okay. Which side does this 5 square root of 3 side correspond to in my kind of formula triangle over here? It corresponds to x. So this thing is equal to x. Okay, right? This is because it's opposite that 30-degree angle. Opposite the 30-degree angle here is x. So this thing is x. Opposite the 60-degree angle, then, it's going to be x times the square root of 3. And then the hypotenuse here is going to be 2x, twice that x. Okay. So then, let's see here. So Maria, what? So how can we find the length of the hypotenuse? We're going to do 2 times what? What's x? Okay, so look at the picture. What is x? What do I say that x is equal to?
5 times square root.
That's right. So how are we going to find the hypotenuse?
2 times 5 times square root of 3.
Yep, which is equal to what? Okay, but I mean, what's that, when you simplify that, what is 2 times 5 square roots of 3? 10 square root of 3. So that's this side. Okay? Just the x is 5 square roots of 3, so we just do 10 times the square root of 3. All right? And then this bottom side right here, Maria, it's x times square root of 3. So that means, how can I rewrite this using our x then? What will it be? Yeah, that's it. Okay, and again, if you're uncomfortable with that, if you're not sure, I mean, you can just type that in your calculator if you want to. 5 square root of 3 times the square root of 3, it's 15, which we shouldn't be surprised by, because the square root of 3 times square root of 3, that's just 3 times 5 is 15. So this equals then 15. So this side right here is 15. Okay, so there's the 3 sides. So here, the power of this is that with the Pythagorean theorem, With the Pythagorean theorem, how many sides of a right triangle do we need to know in order to solve that triangle? We need 2. For the special right triangles, how many sides do we need to know before we can solve the sides? We only need 1. Okay, so now we only need 1 for these special right triangles. Okay, question?
How do you get the 10 times square root of 3?
It's right here?
Yeah.
So it all starts with identifying that this 5 square root of 3 is the x side, right? It's opposite the 30-degree angle, so this is equal to x. This side is the hypotenuse, and according to our little 30, 60, 90 triangle, the hypotenuse is twice x. So if x is 5 square root of 3, the hypotenuse is going to be twice 5 square root of 3, 10 square root of 3. Okay? And then likewise here, this is the x root 3 side. So again, it's just going to be the 5 root 3 times the root 3, which gives you 15. Okay? All right. We are running short on time here, so do you guys want to see another one here, or do you want to try and start the homework, or what? What would you prefer? You want to see another one? No, you're good? All right, I'll get you started on the assignment then here. We'll see how it goes. All right, I'm going to have you guys do, let's see here. We'll just have you do 1 through 8. Okay. Oh, sorry, page 716 to 717. 1 through 8. Okay. 1, 2, 3, and 4, you're just checking to make sure that these sides are in the right ratios, using what we know about special right triangles. 5, 6, 7, and 8, and by the way, 7 and 8, it says you may want to draw the triangle in your answer. You may want to draw the triangle in your answer. Those you got to solve for the missing pieces and stuff. All right, we'll come back tomorrow and see how that goes.